Okay, so today's quiz that we'll start class with. No, I'm kidding. Questions? Questions? Yeah, I didn't get a chance to. Questions about Cal 2? Questions about Cal 2?
Yes.
Oh, okay. Number 8, and you just did a U sub? That's okay, did it work? Did you take the derivative and it worked? Okay. Yeah. But it would have worked, it probably would have worked with partial fractions also.
How did you do that? How would you do that if you did partial fractions on one?
You do long division first?
The powers are the same.
Yeah.
That's right. Okay.
It probably right after the long division it's over. I don't think you have to do partial fraction. Well, you wouldn't. Is that good?
Yes.
Okay.
Yeah, on 29.
On 29.
I understand like all the way through it all basically.
Mm-hmm.
It's just when you have like the antiderivative of the first part, like the 1/3 natural log of x minus 1 minus the 1/6, and then the second part of it. I don't understand that.
Where?
This part, because I was trying to watch your video and I just couldn't. I don't know. I got stuck here at the same spot, and then I went to the video and it just I kind of got confused, and so I just thought I'd ask.
So where do you want me to take it from? Like
From like right here.
Like, you understand how I got that or no?
Yeah, no, I understand this because it's
Just what to do with this right here?
yeah.
Okay. So let me just put it up here and see if this is what you want. You want me to do the integral 2x plus 4?
Yeah, plus 4.
Over
X squared plus x plus 1.
x squared plus x plus 4?
Plus 1.
Plus 1. So if I do this, you'll be happy.
Yeah.
Yes? Okay.
29?
Is that the actual question?
It's part of number 29, I think, right?
Yeah.
So do you want me to do what I did on the video, or do you want me, because I don't remember what I did in the video. I'm just going to look at that as if it's a brand new problem. Okay.
Yeah.
So if I were looking at that, or if you were looking at that, what would you do? U sub? So you're saying U sub, like make U the bottom and then try and force the top to look like that, the derivative of that? Okay, that's what I would do also, as long as this doesn't factor, which it does not, right? X squared plus x plus 1 doesn't factor, so I agree. Let's do that. So I'm going to let U be x squared plus x plus 1, and du is equal to 2x plus 1 dx, right? So I just need to make the top look like 2x plus 1. So I'm going to add and subtract 1. So I'm going to come in here and I'm going to go, it already has 2x, right? That's why I didn't need to worry about that? You see it now? Yes? So I can stop? Plus 1 minus 1, and then we still had here plus 4, and then over x squared plus x plus 1 dx, like that. If I put these two right here on top of this, then I have U sub. If I put -1 plus 4 on the other one, split it apart, then I'll have an integral with just a constant over an irreducible quadratic, which I would complete the square on. Yep. So this would become integral 2x plus 1 over x squared plus x plus 1 dx plus integral, I would have 3 up here, right? 3 x squared plus x plus 1 dx. So this one's done, right? Natural log of absolute value of the denominator is the antiderivative of this. And then over here, complete the square. So you want me to go complete the square? Y'all want me?
You're good.
You're good. Anyone else want me to keep going? Yeah? Okay, so I'm going to do this one right here. This one's done? Check? Yes, okay. All right, so on the other one, complete the square. I've got to take x squared plus 1. I'm just going to do like scratch work over here. I look at the number in front of x, which is 1. I take half of that, right? All right, that's my first number. I mean, it's just a half. Okay, I don't have to do anything. Then I take that half and I square it. That's 1/4, right? That's another special number. So now I'm going to come in here, I'm going to write x squared plus x.
Minus a fourth.
Other way around. Plus a fourth, minus a fourth. Okay, for completing the square, you always do the plus one. Always the plus first. And the reason why is because when it breaks down to be something squared, right, it's going to be like this one, it's going to be x plus a half, right, squared. When you get that, when you actually square this, that 1/2 and 1/2, that will always be a positive number, even if these were both negative. So that's why it has to be the plus. So this is going to become right here, x squared plus x plus a fourth minus a fourth, and then I had plus 1 there, right? So there's my hidden 0. These three guaranteed to factor to be x plus a half squared, and then these two together become 3/4. Any questions? We're good? So that integral right there is now going to turn into, this one right here is going to turn into the 3 on top, and then x plus a half squared plus, I guess I'll do root 3 over 2 squared. That's just to help you see that this looks a lot like u squared plus a squared, right? So there's a formula, especially if we pull this 3 out. We have a formula for 1 over u squared plus a squared. It is arctan. So 1 over a arctan of u over a plus c. So we could get, you get from here now? Yeah. This would be, I'll write the answer. It would be 3 times 1 over a. A is this, right? It's 1 over root 3 over 2 times arctangent of
x or u over a.
what's
So
u
x
for
plus
us?
1/2.
X plus a half over root 3 over 2. And then you can flip it and bring it back through. But now the reason why I went so quickly with this part is because if this is u, if I did a quick little substitution, what would du be? Just 1, right? So let's just say for the sake of argument here, if that's 3, then this problem would have worked out the same, except I would have scaled it out by 1/3, because I would have to have taken care of that. But I should never have to worry about that on a problem like this. When I complete the square, I should never have to worry about a number other than 1 out here. Why? That's what we actually need to have before we complete the square, right? We had to have a 1 out here anyway. So that should never present itself as a problem. All right. We good? Okay. All right, well, let's see. What's our calendar look like? We've got a test next Thursday. The big test, right? And between now and then, we need to do 5-2, 5-3, 5-4, 6-6. 6-6 is going to take us 2 days, so that's going to be Thursday and Tuesday. All right. We'll talk about it on next Tuesday. We'll talk about whether or not we're going to put all of 6-6 on the test. We might just do, let's just say that officially. Whatever we finish this week will be on next Thursday's test. What we do on Tuesday next week will not be on Thursday's test. That sound good? Okay. That way you have time to do the homework for that. And all right, so today we're covering 3 sections in 1 day, but it's not like, we're going to blow through it and skip over all the, details. We can do all these in 1 day because we've talked a little bit about this. The concept, the principle is pretty clear, all right? It's not like partial fraction decomposition. We just want to know now what those numbers on the ends of the integral meant, right? That's what we want to do. So 5, 5-2, 5-3, and 5-4 deal with what's called the definite integral. And I'm just summarizing all these sections. Now, I'm going to put definite integral here. I'm going to put versus the indefinite integral. Which is what we've been doing. I don't know if I've stressed that word to you while we've been doing it, but we've been doing indefinite integrals. An indefinite integral looks like this. Integral, function, dx. Our answer has always been its antiderivative, right? Capital F, remember the relationship between capital F and little f? Okay. The antiderivative of little f is capital F, and then plus c. The reason why we would call this an indefinite integral is because what we're doing is we're finding an answer, which is a function, right? But the plus c means that there's a family of functions. So we don't have a definite answer, do we? We have a function within some family, but we haven't nailed one down. Now, if someone gives us some initial condition, we could actually tell you exactly which function, right? Like if I told you, f of something was, f of 0 was 2. Remember how we did that? Yeah. Okay. So this is why we call this an indefinite integral. Our answer here, this answer, is a function. Now, we compare that to what's called a definite integral, which is the same symbol, but now we're throwing these numbers on here. So we're going to call this a, and we're going to call this b. Here, a and b are numbers. And this is also going to give us some answer, but it's not going to be a function. It's actually going to be a number. So this will be a numerical answer. And so I will write here equals, and I'm going to leave a space intentionally. And I'm put capital F of B minus capital F of A. Now this relationship here, okay, of this integral meaning this, is actually comes from what's called the fundamental theorem of calculus. Fundamental theorem of calculus. There's two versions of the fundamental theorem of calculus. This is commonly referred to as the second version. But this is, whenever we have fundamental theorems in mathematics, when you say fundamental, you mean very important, right? This is a foundational theorem from calculus, that there is a connection between the antiderivative and its derivative, and somehow all we have to do is be able to find this antiderivative and then somehow plug that number, whatever it is, into the antiderivative, plug this number into the antiderivative, and subtract those two numbers. And y'all remember what that represents for us?
The area.
The area. Did we talk about that? Do you remember? No, I didn't?
Yeah,
I thought we did the Riemann sums and kind of showed you that, yeah. We voted, right? And I said, do you want to see a little bit of what this really means? And we did look a little. Okay, so I'm going to get rid of the indefinite so I can talk more about the definite. So what this means geometrically is that if you take some function, all right, and you start at a left endpoint of A and end at a right endpoint of B, by finding the antiderivative, okay, so you still, look, we can't get away from the fact that you have to find the antiderivative. But now, once you find it, you're going to plug two numbers into it and subtract them. Once you do that, that number that you get here means what? It means, it represents this area, okay? The area right here would be equal to this right here. And we're not going to prove this because it's a fundamental theorem of calculus. I didn't prove it until I was in a couple of theorem proving courses in mathematics. So we're not going to prove the theorem here, all right? The book does go through some, attempt at proving it. So you can read through it if you want. We're just going to take it on faith that that's what it's going to get us, okay? Now, I do, however, want you to understand the symbols, right? Because I thought that was important. When we were talking about this before, we said what we're going to do is we're going to imagine that there's a rectangle in here. And we even came up with a formula. I remember doing it, right? With you? We came up with a formula for the area of this rectangle. Basically, we said that the width of this rectangle, I'm going to blow that rectangle up. We said that the width of that rectangle, we called that, it was the change in x, delta x. It was the change in x. It was actually, if you go back and look at the formulas, it was b minus a over n. You can go back and look at the lectures if you want. And then the height of this rectangle was the function's value at some point. We could pick the right or the left endpoint, or anywhere in between. Does that ring a bell to you? All right, so then if I wanted the area of this rectangle, it would be this times this. So the area of that rectangle would be f of x times delta x. And then what we did is we said, well, we just want to add them all up, right? We add them up. When you add things in mathematics, we use this symbol, the summation symbol, right? So we add up however many, 100 of them, 1,000 of them. And then what we do is we say, we're going to add up an infinite number of them. So we're actually going to have the width of these rectangles is going to get smaller and smaller, so we get more of them in there. And if you take the limit and you let the number of rectangles go to infinity, right, then you have the true area. And that's where that symbol comes from. So this right here, this symbol, is kind of like this part of it. It's the sum. F of x right here is the height of each of the rectangles. And dx is what we call the differential, is the infinitesimally small width of each rectangle. So each one of these is an area. Do you all see that? That's an area. And you add up forever, which is this, an infinite number of rectangles. Understand the symbology here? Okay. Is that a word?
Symbolism. Symbolism. Symbology is not a word.
You sure?
Positive.
I'll check on that. You sound too sure. You sound too sure. You're going to bet your life on it?
I would.
Okay. All right.
I wouldn't say
Did you
that.
bet your grade on it?
Or would you give me a much better grade? Yes.
All right. Can I look in like an Urban Dictionary?
It is
No.
a word. It's a word. It is a word. It's a word.
Okay.
It's a word. It's a study of use or symbol.
All right. Anyway, let's. Okay. So the connection between the picture and this symbol, everyone understand that? That'll become very important later when we're trying to find volumes, is to be able to take a picture and turn it into an integral. And as long as we can come up with a formula, okay, like here, see how we came up with this formula for the area? And we said just add them up. How do we add things up? Integral, right? So as long as we can come up with a formula later, we'll just turn to the integral at the end, all right? All right, so that's what it means. It represents the area under the curve. And I left a space in here for a reason, and that's because when you're doing definite integrals, what we like to do, is first find the antiderivative, right? Because that's what we've been doing this whole time. So what we like to put here is just capital F of x. Okay, so we're going to say, hey, look, someone wants us to find the area under this function, right, between a and b. All right, first I'm going to find the antiderivative. And then next to it, I'm going to put a bar. I'm going to put b and a. And this just reminds me that once I find the antiderivative, I need to plug b into it, and then I need to plug a into it, and subtract the answers. So this symbol means this. Okay? It's notation. That's all that is. With me? All right. So let's do an example. So as an example, let's find the area under f of x equals 1 over 1 plus x squared on the interval -1, 1. So I'm gonna draw a quick picture of this function. I'm going to graph it, all right? And do it by hand because it shouldn't be too hard to do. What's the value of the function at 0? 1? What's the value of the function at -1? 1/2, right? So at -1, I'm at 1/2. And what's the value of the function at 1? 1/2 again, right? And should we get another one, or do you think that's enough? What do you think it does? Yeah, let's try something else. Let's not go to 2, because 2 is outside of our interval, right? But I mean, if you did do 2, what would it be? 1/5?
Yeah.
So it'd be smaller. So it looks something like it's going down like this over here. It's going down like that. Agreed? As x gets bigger, this ratio gets smaller, doesn't it? Approaches 0. All right, so pick a number that's less than 1, like what, 1/2? So if I do like 1/2 squared, I get a 4th. 1 plus a fourth is 5/4, and then 1 over 5/4 flips, so 4/5. So at 1/2, I'm up here at 4/5, which is pretty close to 1. Then the same thing would happen over here, right? And so what you get is something that looks like this. And what we're trying to do is find the area right there. So because we're trying to find the area under a curve, we're going to use the fundamental theorem of calculus. By the way, this version of the fundamental theorem of calculus is also known as the evaluation theorem. It's the theorem that allows you to evaluate a definite integral. So I'm going to write integral, right? -1 to 1. 1 over 1 plus x squared dx. And I started with one that I thought would be easy.
Yeah.
Is that an easy one?
Yes.
Arctan?
Yeah.
Arctan x. That's the antiderivative. But I'm no longer going to put plus c. I'm just going to put a bar. I'm going to put a down here and b up here. I forgot to tell you something earlier. I told you this was a and b, right?
Right.
This is called the lower limit of integration. And this is called the upper limit of integration. Everything else, you should know what it's called. Like this is called the integral sign. This is called the integrand. This is called the differential. Right? We talked about that already. But these two things I never called them anything, so that's what they're called. The lower limit of integration, the upper limit of integration. So you find the antiderivative, great. Forget the c, we can finally throw the c away. And then 1 and -1. And now what I do is I plug in which number first? 1 in first. So I need to do arctangent of 1, and then I say minus arc. What the hell is that? Arctangent of -1. And then you need to know what these are. And you're not going to go get your calculator out. So at what angle is the value of tangent 1? Pi over 4. Pi over 4. Because that's where your x and y coordinates are the same. And so the ratio of the two is 1. Where is arctangent -1? Domain restrictions, yes. Ooh, what are the domain restrictions on the arctan function? Your answer has to be between -pi over 2 and pi over 2. Negative pi over 2, negative pi over 4. That's right. So you have to go back to the, I didn't hear you. If you said that, I didn't hear you. Did you say that? Yes. You got to just say it louder if you want credit for it. Don't get mad that I didn't say it was a good. Oh, okay. All right. I just didn't hear you. Okay, so this should be negative pi over 4. And those two add up to be pi over 2. So the area is exactly pi over 2.
And we don't have to write any units, right?
It's unitless because we don't know what things are measured in. Now, of course, if this was like in feet, then we would say like square feet. If it was miles, square miles, right? So it'll be a two-dimensional unit because it's area. We all right?
When you say the area is pi over 2, just thinking like from 0 pi to pi over 2, so it's all of the first quadrant?
No, no. It's what I'm saying is that, like, if I give you a rectangle, and I say this is 2 and this is, let's say 3, you know, what's the area of this? 6, right? What's the area of this red? It's pi over 2. See, it accounts for all this weird curvature, and that's pretty awesome. We can get the areas of pretty complicated things. Okay, that all right? All right, let's look at another one. Let's do, I don't know, sine? Let's do sine. Let's find the area underneath the sine curve. And let's look at one period of sine. Sine goes from 0 to 2 pi, right? That's one period of sine. So let's go ahead and find the area. So what's the integral I set up? Integral, lower limit,
0,
upper limit,
2 pi,
okay. Integrand,
Dx.
okay. And then we'll just find the antiderivative. So what's the antiderivative of sine? Negative cosine, x, lower limit, upper limit. Now we're always going to do 2 pi in first, then subtract what we get when we get 0, right? So because things start to get a little more complicated, not necessarily in this problem, a lot of times when I'm doing things, I'll just set up the two pieces first. Like parentheses, here's going to be my capital F when I plug B in. Parentheses here, here's what I'm going to get when I plug in A into capital F. So first I plug in 2 pi. So negative cosine of 2 pi, which cosine of 2 pi is 0. No? No. What is it? 1? That's the same as cosine of 0, which is 1. But then there's a negative. So this is negative 1. Minus, okay, I never did this one. Negative cosine of 0. Cosine of 0 we just said was 1, but then negative. So negative 1 again. And that's just negative 1 plus 1, which is 0. Oh, come on, that can't be right. Yeah, let's take a look at this picture. Well, it's got to have some area, right? If the area is 0, there's sine, right? On one period of sine. If the area is 0, then what's happening here? No.
Negative and positive areas.
Yeah, we're actually getting somehow this integral, it counts things below the x-axis as negative, even though areas should never be negative, right? So it's counting this as like positive area and this is negative area, and then they're canceling each other out. So that doesn't help me know what the area here is, does it? So what we want to try and do is account for this. So why don't we, instead of doing this, just go to here, integrate to there instead. Whatever that area is, if we double it, then we're going to get the area, right? So this is something we always have to be aware of when it comes to these definite integrals, that it will count things below the x-axis as negative and things above the x-axis as positive. Now, why does it do that? Well, because remember, each rectangle, how wide was each rectangle? Dx, right, or delta x, which is a positive number. But then the height of the rectangle was f of x, wasn't it? And if that height is positive, then we have a positive times a positive, that's going to be a positive number. But if the height of the rectangle comes from the function's value and it's below the x-axis, then that's going to be a negative number, right? And negative times positive will be negative, so it's going to count that area, that rectangle as negative area, and then they cancel each other. Got it? So that's why it's doing it in the formula. All right, so let's do this. Let's change it up. This is the correct answer, okay? If someone asked you to find the area under that from here to here, you would say that because that's the net, right? But what about if they say find the area here to here? Same problem, but from here to pi. So that would change this to pi, this to pi, this to pi. How does that change this answer? Cosine of pi is -1, and then negative, so this becomes +1 now. And this one doesn't change. So your answer would be 2. Yes?
What happens if it goes to like infinity?
If what goes to
Like
infinity?
0 to infinity? Like the range? Would that still be?
Oh, what if I change the definite integral here and have a limit that goes to infinity? That's 6.6.
Okay.
That's what we start covering on Thursday. If not today, we might get it today. It just depends on how quickly we want to move through this. Questions? Okay, a couple of, let me bring up my notes. I didn't have these opened yet. No, just use it, just leave it as a number. Just a number is fine. What is this? Where is it? Okay, so this is everything. Uh-oh. Whoa. That's not it. 4.7. I've lost it. Is it in my Riemann sums? There we go. Properties. We need to talk about some of the properties of definite integrals. And I'll make this bigger. See if any of those look interesting. So just take a look on the board real quick. Look at that definite integral. Integral from 0 to 2 pi of x cosine x dx. The graph of it's given there. All right? We're going to get some positive area and some negative area, right? How would you actually find the antiderivative of x cosine x? Integration by parts. So that integral would require integration by parts before you could do it. Would y'all like to work through that? Yeah. Do you want to try it? Yeah. Yes? Go ahead. See if you can do that one. The definite integral from 0 to 2 pi of x cosine x dx. My hint to you is do all the integration first. Get this guy first. All right, that's the first part of the problem. Then you go and plug the numbers in. All right? While you're doing it, I'm going to work it out on the board. That way I don't have to write it down. The homework? It's a lot of work, huh? You're better off for it, though. You're a better man now.
In the math world.
No, overall. Just overall. You're a better person for having done that.
You got some gray hairs now.
I know, man.
That's right.
You gotta use it. Was it just for men?
Yeah, Cal too.
0. I missed the minus between.
All right, so y'all done?
From what down?
I was making the mistake of not putting in the entire antiderivative, although I put x squared.
For those of you who are done, how would you find the area of each of those regions?
Restricted?
Okay, so you think you could do that? Do you think you could figure out where to restrict it?
Yeah. Yeah, you can. The x-intercept.
Okay, so you think you can find them?
The root? Yeah.
See if you can.
Come on, Matt, you can do it.
Who's still working on this? You got a couple of people still working on this?
Calculator won't let me down. 0.
Your answer should be 0, which means that the area above the x-axis in that picture is equal to the area below. It's kind of interesting because it doesn't look symmetric, right? All right, so you did your integration by parts table, you figured out your antiderivative first, plus c still. Then I came over here, I said, let's throw that over here, no c, your two endpoints, plug in, you get 0. But my question now is, how could you find the area of each of those regions? So what I'd like to do is see if we can visit the concept of figuring out when x cosine x would be 0. These would correspond to the x-intercepts, right, of that function. So that's a trig equation. What makes this equation true? So you have multiplication here, right? So you can just split this up. X is 0 is one answer, and then cosine x is 0 is the other answer. And I'm only looking for solutions between 0 and 2 pi, right? So what are the only places that cosine is 0 between 0 and pi? Sorry, 0 and 2 pi. If x is pi over 2 and 3 pi over 2. Right? The only places on the cosine curve where you get 0 is at pi over 2 and 3 pi over 2. So those x-intercepts are those. So what we would need to do, if we were going to do this correctly, not correctly, but in order to find the area without taking into account the negative part and not letting it cancel us out like it did, is we'd have to first do an integral that goes from 0 to where? Pi over 2 of x cosine x dx. Then we would have to do another integral that went from pi over 2 to 3 pi over 2 of x cosine x dx. And then we would have to do another integral that went from 3 pi over 2 to 2 pi of x cosine x dx. The good news is that we know the antiderivative of all these, so it's just a matter of plugging things in, right? That's all this would be. So let's do this one. The antiderivative of this one, let's call this one 1, we'll call this one 2, and we'll call this one 3. So if I do 1, it's the antiderivative, which I believe was x sine x plus cosine x. And I evaluate that, this time from 0 to pi over 2. So plug pi over 2 in first. Get pi over 2. What is sine of pi over 2? 1 plus what's cosine of pi over 2? 0. Minus, and then now I plug in 0. So 0's out here. Cosine of 0 is 1. So you get pi over 2 here minus 1. Yeah? Pi over 2 minus 1? That's the area. So if you look at that over there, that first little arc above the x-axis has an area of pi over 2 minus 1. Is this a positive or a negative number? Sure? Pi is 3.14-ish. Divide that by 2, it's a little bigger than 1. Take away 1. So that should be a little positive number there, right? Now let's do this one. Sorry, we did that one. Let's do 2. Okay? So for 2, I'll put 2 right here. For 2, it's the same antiderivative. Whoa. Sine x plus cosine x. This time pi over 2 to 3 pi over 2. So I'm going to plug in, let's see, pi over 2 in here. Didn't we just do that? What happened when we plugged pi over 2 into this? We did it right here, didn't we? We got this? Wasn't it that first piece? So it's going to be pi over 2. We know that already. This piece will be different, right? Shit, hold on. I meant it the other way around, sorry. Thank you for giving me that look. 3 pi over 2 goes in first. That one's new, okay? So what's 3 pi over 2 in here? 3 pi over 2, sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. Then minus, now this is the one that's pi over 2. Pardon me. I apologize. Questions on that? So this is negative 3 pi over 2 minus pi over 2, which is negative 4 pi over 2, so negative 2 pi. It's negative area, right? So we'll turn it into a positive. But just in terms of the picture, that piece that goes underneath, okay, because it's negative, because it's below the x-axis, it's negative. But if I just say, hey, what's that area? And we're just like, negative doesn't make any sense, then the answer would just be 2 pi, wouldn't it? All right, let's do the last one, 3. So we're doing x sine x plus cosine x, and evaluated at 2 pi up here and 3 pi over 2 here, right? Okay, let's do 2 pi. You get 2 pi, what's sine of 2 pi? 0. Plus, what's cosine of 2 pi? 1. Minus, now plug in 3 pi over 2, which we just did that, didn't we? What did we get when we plugged 3 pi over 2 in? We got negative 3 pi over 2? So what is that? 2 pi and 0 is gone, right? So that's 1 plus 3 pi over 2? We good? If I were to take these right now and add these all up together, I should get what?
0.
0. Let's just try it. Let's do this one with this one. Don't the ones cancel?
Yes.
What's pi over 2 plus 3 pi over 2? 2 pi. So I have 2 pi when I put those two together. Now put it to this. You get 0, okay? But now if we wanted the total area and counting everything as positive, then what we would do is we take this number, change that one to a positive, and then take this number, right? So everything that's above the x-axis, you just keep the answer. Anything that's below the axis, just change the sign to positive. So if we wanted that, we could say the answer would be what? Pi over 2 minus 1 plus 2 pi this time, and then plus 1 plus 3 pi over 2. And combine anything together, what is this? 4 pi? You getting 4 pi? 4 pi. Bless you. Yes, you could do the absolute value. But not, you don't want to do the absolute value of the function inside. Just take the absolute value of the answer. Yes. All right, let's talk about some of the properties of definite integrals. The first property. is that the integral from a to a of any function is 0. Does that make sense to you? Why is that 0?
It's like we're not going anywhere.
Yeah, that's right. You have a function, you're saying, okay, I want to go from here to here, and that's just a straight line. And what's the area of a line? 0. A line has 0 width, so the area should be 0, right? That makes sense then? Okay, the integral from a to b of a function is equal to negative integral from b to a. So what does that mean? If I'm trying to find this area, right, whatever this area is, it's equivalent to the negative of b to a. So that's flipping these two, right? It's like instead of integrating from here to here, we're integrating from here backwards. What happens is, you know, in the formula dx, the width of the rectangle is a positive number. If you integrate from b to a, then dx is negative. And that's what changes the sign. All right, so that's all that one's saying. This next one, what's the integral of a constant? So you have a constant function. Here's the constant function, k. That's how high it is off the ground. You integrate from a to b. You want to know this area? Well, you can do that without any calculus, can't you? You know how wide it is. It's b minus a. You know how tall it is. It's k. So it's k times b minus a. Yeah? All right. We knew this already. If you have a constant in front of the function, you can pull that out. So you can find the area with the constant in there, or you can take the constant out and multiply it at the end. Next one. If your function is positive, then the area must be positive. Do you agree with that? If your function is above the x-axis, then the answer, your area should be positive also. If the function is negative, then your area is negative. The integral is negative. If you break up a number line, then you can break up the integral. We just did this. This property 7, when we broke up between 0 and 2 pi, we broke it up into 3 different integrals. That's what that property says. You're allowed to do that.
Sometimes it's easier like that. Do you mind showing 5 and 6?
Sure. Okay, so like if your function is positive, greater than or equal to 0. So I have to draw a function that's above the x-axis. Do you agree that this function is greater than 0 or equal?
I didn't need explanation. I was just writing.
Oh, okay.
Sorry, that's transfer.
Oh, okay.
Yeah, apologies. You can explain it if you like. I won't stop you.
Well, just remember, all these properties are in the book, so there's not really, I mean, you don't necessarily need to copy them down. And these notes are online?
No.
These aren't. For this one? For Riemann sums, I never put the notes on?
Your previous class ones up there, like
I'll
you
look.
said, but
I'll look.
I haven't seen
So if the function is above the x-axis, then the area has to be positive. If the function is below the x-axis, then your area has to be negative. 7 splits them up. If you wanted to find out like what, you're going to get a negative area. Your answer is going to be right, it's just going to be negative. But if it's like negative 2 pi, the area is really 2 pi. Right? If f is even, now this is an important one. If f is an even function, then we have something nice. So first you have to remember what it means for a function to be even. Geometrically, even functions are reflections of themselves over the x-axis. Oh, sorry, I meant to say y-axis. So an even function, if I take a function and reflect it over the y-axis and it lands right on top of itself, we call that an even function. So if you ever want to integrate, notice it says there negative a to positive a. not a to b, only negative a to positive a, then whatever this area is, and this area is, there's also another version of it over there, right? So it's just whatever this is, it's going to double. Whatever this is, it's going to double. Whatever this is, it's going to double, isn't it? So that's what that property says. If you want to integrate an even function only from negative a to a, instead, you can just go from 0 to a, so you can just go from here to here and double the answer. Double the answer from 0 to a. Make sense?
Yeah.
That you could do that? Okay. How do you think this works for odd functions? What does an odd function look like? Sine is odd? You all agree sine is an odd function? Okay, so let me draw sine. It would go like, let me say from here to here. Let me just draw that much sine. If I did it here and here, it's the opposite, right? So like if I went from negative a to positive a, this area over here is negative, but on the other side it's positive, and this area here is positive, and on the other side it's negative. So what should that be? If you integrate from negative a to a of an odd function, you should get 0. That's what the next property says. If f is odd, look at that, I even used the sine function there. If f is an odd function, then the integral is 0. Now, that's great, but how can you tell if a function is even or odd just by looking at it? Like not looking at the graph. You can tell by looking at the graph, but if someone just gives you a function, how do you tell if it's odd or even? So let me give you an example. Is f of x equals x squared, or x cubed plus x squared, odd, even, or neither? Neither is N-E-I-T-H-E-R, not I before E, except after C. How do you check it? Here's what it means to be even. For a function to be even, here's what must happen. F of x has to be equal to f of negative x. Which means that if you plug x into it, you get the same thing as plugging negative x in. So if I plug 2 in, I should get the same answer if I plug in negative 2. To be odd, when I plug a negative in, I shouldn't get just the function, because then it would be even, right? I should get the opposite. And if what? Then, yeah, then neither one of these would hold.
You would just get like a complete
Yeah.
answer on the side.
Let's check this. Let's see what happens. What is f of negative x right now? If I take a negative number and plug it in here, what happens if I take a negative number and cube it? It's going to be negative x cubed, right?
No.
Agreed?
Yeah,
Like if I
same
take
sign.
negative 2 and cube it, I'm going to get 2 cubed but negative, right? Negative 8. Now what happens if I plug in a negative number and square it? It's positive, so that still stays the same. Okay, so first, this is the standard way of checking. You first plug a negative in, see what happens. Then, next to this, just tell me what negative f of x is. So just change the signs of everything. So this is negative x cubed and minus x squared. And now what we're going to do is check, are any of these equal to each other? Is this equal to this? Are these the same?
Yes.
They are?
No.
No. Look, if you plug in 1 here, what do you get? 1 plus 1, right? You get 2. If I plug in 1 here, I get 1, I get 0, right? These aren't the same? So it's not even. Is it odd? So I have to check, are these two the same? Almost, but that minus, right? Those two aren't the same. It's not odd either. Therefore, it's neither. So given a function, it's either odd, even, or neither. Questions? If I change this to a 6, what does this do? When you take a negative number and raise it to the 6th power, it doesn't matter, right? It's going to stay. And then here, stay. If I change the signs, it's negative this. So you check, are these two the same? Yes, it's an even function. These two are not the same, right? Okay. How are we doing on time? Oh, we got plenty of time. Plenty of time. So one of the more profound questions, go ahead, man. $5. I can't do that, actually. I can't gamble in class on camera. So I withdraw that statement. But go ahead. I want to see if you're going to make it or not.
Easy 5.
Come on. Oh, you got rejected by the pillar, which has been there since the building was put up.
It's the win.
All right. Okay, so, you know, one of the more profound questions that we asked as we were progressing mentally as a species is, you know, we have a really easy way of finding the area of rectangles. It made sense to us to define it as length times width. The integral is allowing us a way to find areas of things that are not so nice, right? That have weird shapes to them. I wonder if this will help us figure out what the area of a circle is. Now, we all know the area of a circle. It's pi r squared, right? Someone gives you a circle, they give you the radius, everyone will say area is pi r squared. But that, yes, that's true, but that eluded us for a long time. The Chinese attacked that problem. They used the method of exhaustion. They came up with all these little approximations. I showed that to you. And they got some pretty good approximations for pi, too. 22/7 is a good approximation, but it's not pi. So it wasn't good enough. I wonder if today, on the 1st of, March 2016, we can use what we've learned to actually come up with that formula on our own. What would that require? Think about this picture. I want to know the area of a general circle. We know what the answer should be, but I want to know, with what you've learned in this class, if you can come up with that formula. Anyone have any recommendations? How do you mean? You want to cut it in half and look at just half the circle? Which half? You want to look at top half? Okay. Okay, so you're looking at maybe trying to just find the area of that and then doubling that answer? Yeah, I think that's a fair way to go. You want me to orient this thing like where this would be like the origin maybe, and that would be like the x-axis here and the y-axis here? You want to split it again? You could? Y'all want to split it again into a quarter? Okay, we'll split it here. All right, I'm up for that. So you're saying let's find the area of this. That if we could find the area of this, whatever this is, we just multiply that times 4, and that should be the area of a circle. Okay. Well, that, I'm on board. Now what? It's a good suggestion. Okay, the integral, it's going to be an integral. Hopefully you see that. It's an integral, right? It's the area. And you said 0 to r. Very good. We're going to go 0 to r because we know that the x value is going to have to range from 0 to r, isn't it? This is an arbitrary circle. The radius is r. Okay, good. Now, what? We need a function. Do you know the function that draws the circle? Do you know, okay, yes. Do you know any equation that gives you a circle?
Is it
X squared, keep going, plus y squared, that's the unit circle. No, you're so close.
Is it a letter?
R squared. r squared. X squared plus y squared equals r squared. That is the general formula of a circle that is centered at the origin with a radius of r. That actually comes from a more general formula that you hopefully, now that you've seen this, remember. This is the more general form of a circle. This is a circle with radius r and center hk. So of course, if we're going to want to orient this circle in the center of our grid right at 0, 0, then h and k are 0, and it becomes x squared plus y squared equals r squared. This is the one everyone should remember. That's just one special case. Hey, I'm good. The only problem I have with this so far is that that right there is not a function of x. Because circles fail the vertical line test, don't they? So that's not a function of x. Yeah, the way we know that is if we tried to solve for y here. Let's try and solve for y real quick. If we try and solve for y, we would get y squared equals r squared minus x squared, wouldn't we? And then if you try and get y right now, I'm going to have to do plus or minus the square root of r squared minus x squared, yeah? So what happens here is if I do the plus, that's going to draw me the top half of the circle. If I do the minus, it's going to draw me the bottom half. And the reason we know that is because this answers the y coordinate, isn't it? So if it's positive, then it's the top. If it's negative, then the y's are below. Make sense? So really, if we're looking at this piece, we're at the top, right? So we can look at the positive, right? We don't need to worry about the negative. So what is the function that we need to integrate? Square root r squared. Oh. How are you going to integrate that? Trig sub. That's a trig sub. It's not arcsine. I don't know if that's what we're saying. If it's 1 over. Oh, yes, yeah, okay, yes. So we can do this with trig sub, couldn't we? Let's do it. What's the trig sub if we have, the variable here for us is what letter? No. Well, okay. X is the variable. X is the variable. R is the A, isn't it? Yes. R is really the A. So the appropriate trig substitution for this is x equals a sine theta, which for us is really r sine theta. Remember that r is a fixed number, right? R is fixed. And then we go through and we say dx is r cosine theta d theta. And then the square root part of this is r squared minus x squared equals, what is it? R cosine theta? We've done this before. And now I go rewrite the integral. What does this integral turn into? Integral from 0 to r. You know what? Let's do this. Take these off because we're just going to find the antiderivative first. Okay? Let's just find the antiderivative first. So we're integrating this. We'll come back to the definite integral after we're done with our integration. This turns into the integral, what was it? R cosine theta times r cosine theta again? D theta. Good. And that's just
R cosine theta squared.
So we can square the r and the theta, can't we? Right. R is a constant. Pull it out of the integral. R squared, that's very promising. Cosine squared theta, d theta, right? And how do you integrate cosine squared theta, d theta? Power reducing, good. 1/2. So this is going to be r squared integral. You said this is going to turn into 1/2. Can I pull that out? Yes. 1/2, and then it's two things now, right? 1 plus cosine 2 theta d theta. Now, find the antiderivative of each of those. term by term. So I've got, let me write r squared over 2 out front instead of that. Antiderivative of 1 theta, antiderivative of cosine 2 theta. 1/2 sine. Y'all learned something. Y'all actually learned something. That's good. Y'all are following along at like exactly the speed you should be following along here. And then r squared over 2.
Oh, but you have to put it in terms of x again.
Yes,
You have to
yes.
do the reference triangle.
Excuse me, I don't want to interrupt you, but I'm going to. Seriously, that phone right now is more important than proving that pi r squared is the area of a general circle? Okay. No, you're not. You're on your phone, which should cost you 10 points on your next test, right? Yes? Yes or no? Yes or no? I'm asking you a simple question. It's on the syllabus. Do you agree? You're not even going to show me the respect of answering me? Pardon me?
I don't agree with that. It's just a
You don't agree with what? My goodness. All right. We can talk after class. If you don't want to get 10 points taken off, you can talk to me. How about that? Sound fair? All right. So, theta. How do we get theta? Go back to our trig sub, which was x was r sine theta. X over r is sine theta. So what is this? Do you want to tell me what it is? Hello? What's theta? You don't want to share? No? Okay. What is it? Arc sine x over r. And then how are we going to get this? We can draw the triangle, but remember it's 2 theta. So what is this going to turn into? I think I need a new line. R squared over 2. This was arc sine x over r plus, what is this? Sine theta cosine theta. Remember, because this turns into 2 sine theta cosine theta, but then times the half, right? So we need to know what, does anyone need help, like where we are? We okay? All right. Sine theta, we know what sine theta is. But for cosine, I'm going to have to go the triangle. Theta, sine, cosine is this one, right? Right? All right. Geez, this is a lot of work. Okay. We are doing what took thousands and thousands of years to figure out in like 15, 20 minutes here. So this is a good thing. All right, we have arc sine of x over r, and then plus sine theta you said was x over r, and cosine theta was root r squared minus x squared over r squared. Is that it? Are we there? Is that the antiderivative?
Distribute and that's it. Plus,
I could move that through, but I mean, is that the antiderivative?
Yes.
That plus c? We're all good with that? Yeah, I can proceed. Everything's back in terms of x. Okay, so the original integral that we were trying to figure out was the integral from 0 to r square root of r squared minus x squared dx, and we got that that was equal to this, r squared over 2 arc sine of x over r plus x over r times root r squared minus x squared over r squared.
Why is that r squared?
Where?
The last r. Oh, wait, yeah.
shouldn't it be R?
Was it r? Off our circle. Yeah, it was r. I don't know why I put r. Thank you. This is r. Yeah, because this was root r squared minus x squared. This was X and this was R. Yes, thank you. That would have caused a problem later. All right, and then what we're going to do here, that's the antiderivative, and we're going to plug in 0 and R. And the R is going in for what variable?
Why?
There's,
Oh, well, my bad.
what was our variable of integration here? X, right? So we're replacing X with R now. R is a constant. Okay, so I'm going to come in here and I'm going to plug R in first. So let's talk about this. This will be R squared over 2, and then, okay, all right here, R over R is 1. Arc sine of 1. Arc sine of 1. Pi over 2. Good, pi over 2. So this is pi over 2. Plus, over here, R over R, 1. R squared minus R squared. 0, which kills all this off, right? Okay, that's what I get when I plug in R. Minus, now R squared over 2 again, and now let's plug in 0. 0 over R, 0. Arc sine of 0. So where on here is your y coordinate 0? What's the angle that gives you a y coordinate of 0? 0. 0. So arc sine of 1 is 0, plus 0 over R, 0, and then this doesn't matter anymore, right? So all of that doesn't matter. And so your answer is what? No, I had enough here. Your answer to all this is R squared times pi, that's the numerator, over 4.
But then we were multiplying by 4.
That's right. We only looked at that 1/4 piece, didn't we? So multiply that times 4. Pi r squared. There it is. That's it. It's cool, right?
Yeah, that's cool.
Can you imagine like our celebratory, all those pieces?
Well, yeah, I mean, this is, I mean, there's some things that we kind of depended on here. I mean, we had to know some stuff about trig functions, you know, but I mean, I think we can all be satisfied with that being a nice result. Okay, 12:15. We've got, and we got plenty of time. Seeing what else.
I don't ever use back pages 15 either.
Okay, so let me see if I can remind you from Cal 1 about something called the mean value theorem. Yeah. From Cal 1. Let's see. This is what the mean value theorem said, and I'm going to summarize. I'm not going to write it all in detail the way that the book would do it. Just go into index and look up mean value theorem if you want to research this. Okay, so the mean value theorem said this. If you have a nice continuous function that's differentiable, meaning you can take its derivative, then if we connect the two endpoints together with the line segment, that blue line segment has a slope to it, doesn't it? And that slope would represent the average rate of change of the function. The mean value theorem says that there has to be some point in here where if I look at the slope of the tangent line at that point, they must be parallel. So the average value of the function, which is the solid blue, the slope of that line, must be equivalent to the derivative at some point. And you may remember it from this, with this formula. The derivative at some point c equals f of b minus f of a over b minus a. That's the mean value theorem. Here, a is this endpoint, b is this endpoint, and c is some point inside. Does that ring a bell? Yes. Okay, we have a similar thing for Cal 2, and it's a mean value theorem for integrals. Here's how it works with the mean value theorem for integrals. I'm just going to put, for Cal 2, the mean value theorem for integrals. And I'll do it with a picture. If I start here at A, end here at B, then we can now find this area, can't we? That area would be the integral from A to B of f of x dx. That's the area of the red. The mean value theorem for integrals says that there's got to be some point inside here, and it's going to be very difficult for me to find it here, but I'll just kind of guess at it. There's got to be some value here, c, inside, that if I went up to the function, okay, and then just drew a rectangle, the area of the blue rectangle must be equal to the area of the red. Does that make sense that that would be the case? There's got to be somewhere in there where those areas would be equal.
How do you find the point, though?
That would be a little more challenging, but you could. Okay? And we're not going to be asked to do it. I just want to show you this. So what we're saying is that this integral should be equal to f of c times b minus a for some c. All right? There's got to be some c in here that if I take the height of the function there and multiply it times the width of this, which is b minus a, so that's the area of that rectangle in blue, that must match the area of the rectangle in red. Okay? And then you can do one more thing here. You can divide both sides of this equation by b minus a, and you get this formula. 1 over b minus a integral f of x dx integral from a to b equals f of c. So that looks a little bit more like the one that we had a second ago. The derivative at c equals f of b minus f of a from Cal 1. This is more kind of like that. We're saying, look, this the height of this function here, okay, the height of this function at this value c is equal to the area of the red divided by the width of this interval, b minus a. So if these two things, do you see that they're exactly the same equations? Just this thing's got divided through on both sides? Okay? Just be aware. I'm not going to test you on this. I'm not going to ask you problems on this. I just want you to be aware of the mean value theorem for integrals, that there is an equivalent one in Cal 1 and Cal 2.
And we can take the derivative of f of c and find c, right?
You could take the derivative here.
Right, and then just find c, right? Because that would be the c that works.
Yeah, no, yeah, you couldn't. But you could take derivative here and then something would happen here. And you could, that's the way you would go about trying to get what c is, yes. But you would have to be able to compute this area. All right, so as far as homework is concerned, here's what I'm going to recommend you do. Is just go back through your favorite sections. And those problems, just pick a couple of problems out of each homework set, maybe 2 or 3, that you already found the integrals for, that you did when you did your homework. And pick problems that had those numbers on them. And now go back and plug them in and see how you do with the grinding out of the numerical grind that it is to plug these numbers in. So you've already done all the legwork by finding the antiderivatives. And we know, like even from the partial fraction problems, those take a while to get, right? So now you got to go back and plug numbers in. And now your answers should match the answers in the back of the book. All right, so I don't really have a set homework assignment here other than to invite you to go back and practice. All right? 20 minutes. Okay, I'll do one more example, and I'm going to start 6-6, but I'm not going to get into it heavy. I just want to talk about it, just get you thinking.
Professor, which one do we do right now? 5-3?
This was like 5-2, 5-3, 5-4, all kind of together. Yeah.
I was trying to distinguish like when you started and stopped.
Yeah, there was no distinction, I guess. 5-2 is like Riemann sums. 5-3, they talk about evaluating definite integrals, and then 5-4, they talk about the fundamental theorem of calculus. So it's kind of all in one here. Okay, so if you were to take a function like, let's say, f of x equals 1 over x. Or you know what, let's do 1 over 1 plus x squared, because we were looking at that earlier. We found the area of that between -1 and 1, didn't we? Instead, what I'd like you to do is consider it, you know, let's go -1 here. It went up to here, and then it came down, and we stopped, right? Let's not stop, though, ever. Let's just keep going forever. Right? And that's what happens, because as x gets bigger, this fraction gets smaller. It approaches 0, it never gets there, right? You give me any number out here, I plug it in there, I'm going to get a positive number. So it's asymptotically approaching the x-axis, but never gets there. So does it even make sense for us to say, hey, go find the area underneath this graph? Does it make sense for us to go all the way out there? Is the area going to be infinite? Is it going to be finite? Like, what is your initial feeling here?
It'll go to 0.
It'll be like physics. It'll get to a point where it's so tiny that it doesn't matter. It'll be 2 nanos wide. No longer exists. 2 nanograms angstrom.
Yeah, so I see this is where physics and math kind of butt heads a little bit, because in mathematics, in pure mathematics, there is no smallest, okay? Like physics-wise, you know, we can only get to a certain point where we can even look that small, right? But if you say the smallest that we know physically is the blah, whatever you want to call it,
Boson.
okay, then I can take half the boson, and that's smaller than your boson. And theoretically, it's smaller, right? So in theoretical mathematics, there is no smallest number. We can always half something, right? We can always, well, as long as it's not 0. We can't have 0, but, right? So as long as it's a positive number, I can always take half of it, and I can always take half of that, and half of that, and half of that forever. So I will never run out, theoretically. So this is where things we start to go, So I agree, though. Maybe it's getting small, and so small that it doesn't matter. But maybe it's getting small, but not small fast enough, so it does matter. And that's what we're going to play with in 6-6. Is this getting small enough, fast enough, for this not to just still be an infinite area? Let me compare that to something like this. Let's look at the function 1 over root x. So at 0, it's undefined. But at 1, it's 1, right? At 2, it's something. 1 over root 2. So it's getting smaller, isn't it? It's going down. It's getting smaller, right? As x gets bigger, this ratio gets smaller.
Yeah.
So I wonder if that area is going to be finite. You know, is this going to be finite? And that's our question. It turns out, okay, that this area is going to be finite, meaning that if you go forever, that area will never exceed a certain amount. It's going to get closer and closer to something, but never actually overfill. This one is actually going to become infinite. And so the further you go out, the more area you get, and that area actually matters. So without getting into the detail, I don't think I have enough time to actually start setting it up, because there's a lot of notation we have to use. We have to go back to limits. Because what we're going to do basically, don't get all upset. It's not as bad as you think. What we're going to do is this, is we're going we're going to take the limit and we're going to let like b go to infinity. So we're going to say, hey, let's do the integral from a to b, but then let b go to infinity. And that will allow us to figure out what the area is. So stay tuned. And then we also have one more thing to address, which would be, what if you look at the function 1 over x, and I ask you to find the area between -1 and 1? What's the problem? You're undefined at 0. So if you were to graph this, you would have this vertical asymptote like this, wouldn't you? Yeah. This one actually goes this way, like that. So you're looking at like the area here and the area here. It might be 0. Well, we'll see. What if I made this 1 over x squared? It'll go up on both sides like that. Does that have an area or not? So we'll talk about that too. Okay. So there's two different ideas here in 6.6. One is that we're going to let the endpoints go to infinity. And the other one is that somewhere in our interval, we have a discontinuity, an asymptote. Yes?
For setting some of these limits to infinity, are you going to have us do longhand work, or can we just let the old calculus do some of it for us when it comes time to like?
You have to do limits by hand. Yeah. Yes. Like L'Hopital's rule. Yeah. You'll need L'Hopital's rule.
On the test, now that we do,
You're free to go. Let's see. Attendance, I guess. Why don't y'all sign out on your way out? We're so far behind on this thing. I can use the quizzes, but we didn't do one today, so just sign out here. Yes.
on the test, are you going to give us like partial fractions and stuff with a and b now, because we know what it is now?
Probably not. Yeah, I mean, the definite integrals, I don't know, maybe not. I don't know, I have to go look at some of my older tests. I kind of want you to focus on partial fractions, like getting that integral right. Getting the integral. Plugging in is, yeah. Okay.